to you about something that I'm very interested in, and that's space physiology. As Michelle mentioned, this is something that I've been interested in since I was very young. I decided to be a physiologist at NASA while I was still in high school. And what I do right now, essentially, is take care of astronaut health from a research perspective. I like to study what happens to the human body when you go to space, stay there for a long time, and then come back to Earth. As you can imagine, microgravity sure looks like a lot of fun, but it's not very nice to your body. So today I'll give you a very quick overview on some of the physiological systems that are affected by microgravity living in space. And then I'll give you a chance to ask us questions. I know you've got a very excited mission discovery and lots of learning to do. So let's get started. I'll flip the slide.
Sure. Give me 1 second.
All right.
Go. You're all set.
Okay. Let's go to the slide that says, what is physiology?
Gotcha.
Just as it says, it's really the study of the mechanical, physical, and biochemical functions of living organisms. In other words, how our bodies work. As you can imagine, it's pretty complex. So we'll talk system by system, and we'll take questions at the end. Next slide.
Gotcha.
So you've been learning a little bit this morning, and you're going to learn a lot over the next few days about space. So in your minds, think about some of the things that are different about the space environment. Of course, we talk about zero gravity or microgravity a lot, but there's more to it. Next slide.
Done.
Yeah. Without microgravity or without gravity, very simple processes that we're used to on Earth change a lot. So, convection. Have you ever seen a candle burn in space? A flame burn in space looks very different. Forms more of a sphere as opposed to that normal candle teardrop shape. And that's because of a lack of student density. And without hot air rising, cold air sinking, you don't have normal convective currents. Buoyancy, and that's a density thing. About heavier items sinking and lighter items floating. The way that move height is a little different. That's true for spacecraft, also true for the human body. Sedimentation. Without particles settling to the bottom and normal diffusion phase work, but without heavier things sinking to the bottom, that changes the way the nutrients might flow. So a lot of things different in the way that microgravity give body, and it starts with very specific issues such as convection, buoyancy, etc.
Just hold on 1 second, okay?
Okay.
Kill a couple things on my computer. But you cut out just a little bit. I'm going to try and kill some stuff, and hopefully that'll help.
Okay.
Hold on. Sorry, joys of technology, right? All right, I got you back up and running.
Okay, so we're on the slide with the picture of our beautiful International Space Station. And that's orbiting above our heads right now, about 200 miles above us. Sorry, I didn't make a kilometer conversion. But it's a fantastic laboratory. It's huge. It's altogether about the size of an American football field. And the internal volume is the size of a gigantic house. And most of that is totally habitable, it's pressurized, it's living space and workspace. And there's a very, very high-class laboratory space available, and we're doing a lot of science every day there, and I'll talk about that briefly as we go. Next slide. So physiology, does it change in space? You betcha. Next slide. You probably can't read the text on that slide, that's okay. Really all I want you to get from that slide is just about every system that you can think of is affected by microgravity. That includes the eyes, the brain, the muscles, the bones, the kidneys, all of our internal organs, our blood. Everything you can think about in your body is somehow changed or affected by microgravity. Doesn't necessarily mean that it's a bad change, but it is changed. Next slide. Okay, again, this is a little bit of a complex slide. The only point that I want you to take away from this is that we're pretty much staying in space for 6 months at a time. That's where we're pretty comfortable. Some people have to stay in space longer. In fact, the longest during flight on a single flight is a Russian named Valery Polyakov. He stayed in space for 38 flights. Now we've had a lot of other people that have taken multiple trips, and cumulatively they've been in space for that longer. But you know, what kind of things are going to happen to your body? 6 months. That's most being in space. See a lot of changes. Hey.
Hey, let's hold on 1 second. We're getting real garbled. I'm going to kill our video.
Okay, yeah.
That will help. I can remember how to.
We could just go to phone only.
That's true. Tell you what, let's do that. I'll hang up and I'll call you back on the phone.
Copy.
Bye.
Bye.
Oh, much better. I got you 5 by 5.
Okay, so I'm still on the slide with the colored lines.
Yep.
And all you can really tell from that slide is on the far left side, there's a lot of changes that start as soon as you get to space. And some of them are transient, meaning they change, some physiological systems are changed right away, and then they go back to kind of a new set point. We call it a microgravity set point. Some processes and systems take a little bit longer to get there. And then some, we're not even sure when they reach a new set point. They may continue to change. An example of that is that purple line on the bottom, radiation effects. Those are cumulative. The longer you're in space, the more radiation you're going to get.